Swayam Prabha. Digital India. Educated India.
Welcome back. We are going to continue our discussion of design of atomizers. In the last two classes we looked at simplex or a pressure swirl atomizer, the different parameters that go into the design, the degrees of freedom like we said the other day, and the constraints that you have to have your design satisfy. So, those are that is essentially the objective of any design exercise, that you take advantage of the degrees of freedom and deliver a certain performance constraint. We are going to continue that discussion today to look at drop size. If you go back, we really left off at a point where we were able to get a film thickness. We did not go much further than that. So, we are going to today look at drop size as a constraint that you could place on the performance of an atomizer. We will see how to make sense of it. Okay, so, we are going to continue our discussion of design. Now, one of the ways in which drop size has been factored into spray equations is through the use of linear instability analysis. We looked at that. Say for example, in a simplex atomizer you may have let us say this is the exit part, and if you did the reentrant trumpet phase at the exit like we said, you essentially have a liquid film that is exiting your spray nozzle, and this liquid film itself could be swirling. So, if your liquid film is swirling and the swirling liquid film is subject to some disturbances, it could cause the liquid film to break down. So, the way we suggested we could model this in one of the earlier classes is you can develop a dispersion relation governing the linear instability, the growth of small instabilities on this system. That dispersion relation gives you omega as a function of k. K is your wave number. We looked at least 3 examples where we derived this omega, the growth rate, as a function of k, and we find the value of k at which df dk is 0. So, that gives me k star. This k star is the wave number for which the growth rate is maximum, which means that in a very short distance away from the nozzle, that particular wave number is going to dominate the structures, the fluid structures in the liquid sheet or in the liquid film. Okay, and so that gives me, which also implies that 2 pi over k star is the characteristic size of the fluid structure that is most likely going to break off. So, here is a way I can relate the nozzle performance or the parameters of the associated with the flow inside the nozzle to a structure that could likely break off from the liquid sheet, which could further coalesce to form a drop further downstream. So, to start with, I have this linear instability modeling allows me to go from internal flow inside the nozzle to external flow. We looked at the models due to Giffen and Murazov and Xu et al, where you are able to take internal flow, the swirling flow inside a swirl chamber and predict a film thickness, a film swirl velocity, a film axial velocity, and those will form inputs to your linear instability model, which could give rise to a dispersion relation that in turn gives rise to drop size. So, this is following a track of almost completely analytically modeling the system. So, we are only sticking to looking at the system as being enveloped by an analytical model. The other approach, a complementary approach, has been to rely purely on experimental data. Okay. So, while this approach takes us from internal flow in the nozzle to an external spray characteristic such as drop size. Okay, using pure and using only analytical tools for the most part. Other than that 1.17 factor that we put in front of the CD equation, if you go back to the last lecture, everything else was purely analytical and the model worked even without the 1.17 correction factor. Okay. You are just off by about 15%, which is not too bad. Okay. The other complementary approach is using empirical evidence. So, what do I do in this approach? I have, let us say, a fluid line in which I am able to monitor the pressure. I will call this P1, and this fluid is coming into some sort of a spray nozzle that is creating this spray, and let us say the pressure here is P2. So, delta P, P1 minus P2 is the pressure differential driving this flow. So, in return for the pressure differential I could get some Q, which is a volume flow rate, I could get a spray angle theta. So, I will call this theta over 2, and I could get some SMD, which is this outer mean diameter. If you go back to our old notation from PDFs, SMD is essentially D32, which is defined as d cube times f of d dd divided by 0 to infinity d squared. F of d is my drop size PDF, and D32 is defined as the third moment, which is integral 0 to infinity d cubed f of d dd divided by 0 to the second moment, which is 0 to infinity d squared f of d dd. Okay, now clearly you can see this has units of diameter, and this usually has a special relevance when it comes to sprays, because this is the total volume per unit surface area. We looked at this early on, and the total volume per unit surface area has a relevance to a lot of spray applications. So, I can now, let us say we have looked at Q, the volume flow rate, in terms of the pressure, and the Q is not directly related to the pressure, but the way we found Jones correlation, for example, gives us a way to relate C D, the discharge coefficient, to everything else that is related to the spray geometry. Okay. So, I can similarly find a correlation for the spray angle in relation to the other geometry features. We in fact did that, although we found an analytical expression based on inviscid flow theory that seems to work reasonably well. And we also found that, really speaking, in a commercial spray nozzle they do not rely on the fluid mechanics inside the nozzle to give us a certain spray angle. They use Coanda effect, which is much more effective and provides much finer control over the spray angle at the exit. Okay. What we are going to do today is look at Sauter mean diameter and how Sauter mean diameter is in turn related to the properties inside the nozzle. Okay. So, again, like I said, there are two approaches. The first approach is using purely analytical tools such as inviscid flow theory and linear instability theory. That does go fairly close to predictions, fairly close to measured values, but the best bet for most design level tools would be to use empirical correlations, and so we are going to look at a few such empirical correlations today. So, what sort of empirical correlations are available? For SMD in simplex nozzles, in pressure swirl nozzles. One of the first and early works is due to this man Radcliffe, who gave us this formula. Okay. So, just to get the nomenclature right, sigma is surface tension, nu L is liquid kinematic viscosity, m dot L is the liquid flow rate, mass flow rate, and delta P is the pressure difference. Now, we will study this a little carefully and see what we can learn. The first thing that Radcliffe is trying to tell us is that surface tension seems to have a significant effect as far as the sheet breakup is concerned, because the exponent associated with that has the highest magnitude 0.6. Liquid viscosity on the other hand has a small positive exponent 0.2, which says that as the viscosity of the liquid goes up, the drop size is expected to go up, although not very strongly. Okay. As the mass flow rate goes up on the same atomizer, now how does the mass flow rate go up on the same atomizer? It goes up because delta P goes up. There is no other way, because this is only a single fluid atomizer. So, as delta P goes up, mass flow rate goes up, and as a result the increased mass flow rate gives us a outer mean diameter that is slightly higher, but the delta P is raised to the power minus 0.4. So, really speaking, this is supposed to be valid over a large range of atomizers that go beyond just a single atomizer, but if I were to apply this over one single atomizer, I have to figure out how delta P is related to m dot L, and that is usually using the Jones correlation using CD, where you can relate the volume flow rate to delta P or the square root of delta P more precisely, and that gives us some way to relate all these parameters. There is one serious problem and shortcoming with writing an equation like this. That is the fact that an equation like this is dimensionally incorrect. That is, all of your quantities sigma, nu L, m dot L and delta P are all dimensional quantities. So, this number 7.3 is expected to have some weird units to it, such that the right hand side, all of the quantities on the right hand side raised to those powers give you a length scale, give you units of micrometers or some drop size unit, which is what is on the right, on the left hand side of this equation. So, one of the biggest problems with an equation like this is that it is dimensionally incorrect. While it is of engineering use, meaning I can convey information to a fellow engineer through an equation like this, but I will have to give the fellow engineer a lot of other information about what unit system should be employed for sigma, for nu L, for m dot L, etc. Otherwise, the number 7.3 would be different, it would depend on the choice of the unit system. So, there were right around the 40s, 1940s and 50s, there were a lot of these kinds of correlations that were developed that gave us dimensionally incorrect correlations, that in order to reconcile we have to go to some sort of a non-dimensionalization. Okay. So, that was the need for non-dimensionalization comes from needing to convey outer mean diameter like information without needing to convey a system of units, that without being constrained to a single system of units. Okay. So, let us see how to do that. If I go back to my simple model of a liquid film exiting the simplex nozzle, and I want to make a list of all the quantities that are my design variables. So, in this simple problem, let us say list of dimensional quantities that are important. You start to see rho, the density of the liquid, sigma L, which is surface tension, mu L, which is liquid viscosity, m dot L, which is liquid mass flow rate, UL, which is like a liquid characteristic velocity, and let us say D0, which is that distance, the exit orifice diameter. These are all quantities that one would expect will play a role. Okay, so, I am going to transcribe these back on the other end here. So, deriving dimensionally correct SMD correlations involve taking this list of quantities and finding a set of dimensionless groups that are important. So, if I go through this, I have 1, 2, 3, 4, 5, 6. If I go through the dimensionless grouping, I am expecting to find 3 dimensionless groups which are important. How did I come up with this 3? I am expecting to find n minus 3 groups, and for this case n equal to 6, and I have 3 primary dimensions. Now, I can go through the so called Buckingham pi theorem analysis, or I will just write down the result, because this is standard UG classroom exercise. I have the Reynolds number, Weber number, which is given by rho L, and the last one in fact is like our CD. Okay. I will call this alpha, which is essentially m dot L divided by rho L U L d 0 squared. Coming to think of this, the denominator here has units of mass flow rate, okay, it has units of kilograms per second. The numerator is the actual mass flow rate m dot L. Okay, so, if you go back, this essentially represents this is like our x, which is the area of the air core divided by, although not exactly the same, it is like our x essentially. It gives us the effect of the air core at the exit. Now, if you go back, I need we can now figure out a way to correlate all of these variables to their respective dimensionless groups. And the one due to Wang and Lefebvre is the most general in this regard, and what that gives us T here is the film thickness that can be obtained from inviscid theory. Now, these quantities that you see in this parenthesis, actually I need to place that. So, that gives me the dimensionless film thickness. These quantities inside the square parenthesis, this part and this part, are essentially dimensionless groups that are functions of the Reynolds number and the Weber number. So, some combination of Reynolds number and Weber number give us, and alpha give us these groups. So, there is two different approaches to predicting spray performance, one or drop size in a spray actually. One, the use of inviscid flow theory inside the nozzle to give us the boundary conditions to go into a linear instability analysis, and the length scales that are predicted from the linear instability analysis giving us initial estimates of drop sizes. The second approach is to purely go to an empirical correlation based approach, where we relate the input parameters to the nozzle to the parameters of the performance of the nozzle, meaning SMD. So, SMD I can write down a correlation of the form SMD over D0